How's the volume on that? Good? Okay. And volume on me? Down. Better? Better, okay. Alright, hello everyone. I'm Donya Quick. Paul is my advisor. And today I'm going to tell you about this Haskell-based automated composition system that we've been working on. Before I do that though, since I know that not everybody here reads music theory texts for fun, this is everything that you need to know to survive this talk. The previous talk already covered this first bullet. A chord is just a collection of simultaneous pitches. So, here's a chord. Do you guys hear that? A little bit louder. Okay. Better? More! This is new. It sounds like it's coming out from over here. Let's see if I, there we go. Okay. Sorry about that. This probably means the next thing I'm going to do is too loud. So, here's a chord, here's a chord. That's also a chord, it's just a bad one. So hopefully our system doesn't produce too many of those. There are two types of chords that I will be talking about today. The first type are abstract chords, and specifically Roman numerals. This is a notation used by music theorists to classify chords in different ways. You don't need to know any more than that, really. If you see a Roman numeral, there are many ways that a musician might interpret that Roman numeral, and some of the factors influencing their decision are the current key or mode that the music is in at that point in time. Concrete chords, when I use that term, I'm referring to basically these as you see them on the score. So I'll play this for you. So the takeaway from this is that you have three different concrete chords that have all been assigned the same Roman numeral label. And just one last term before I move on. Voices refers to basically the cardinality of the chord. So this last chord has 4 pitches, 4 voices. And you don't need to know why. Just accept it as how the universe works. I mean, that would take up half of my talk, just to try to get everybody on board with that for the non-musicians. Excellent! Now's my chance to lie. So this system that Paul and I have been working on has 2 general steps to it. The first is abstract structural generation, and the second we call musical interpretation. So a complete pass through this system, you start with a grammar, which I'll talk about in a minute, and from that grammar you get abstract chord progressions. So we get sequences of Roman numerals. We can't hear those yet. So we take those sequences of Roman numerals and a tool called chord spaces, which I'll also talk about later, crunch that through a constraint satisfaction algorithm, maybe fiddle with the results a little bit, and out pops a musical score that you can play. So the particular type of grammars that we're using are called probabilistic temporal graph grammars. And these capture 2 important features of music, the first being harmonic structure in the abstract sense, and the other being metrical structure. And what that means is that hopefully you can kind of clap your hands to the output of this grammar and it doesn't just sound disorganized and random. Okay, so first I'm going to show you the math for these grammars, and then I'm going to show you a little bit of the Haskell implementation for them. And hopefully you'll be able to take away the fact that the Haskell implementation actually looks an awful lot like the math. So we start with our set of Roman numerals, and we use this superscript notation to mean a chord with a particular duration. So if you saw a 1 chord with a superscript of 5, that 5 refers to the duration. It could mean seconds, it could mean minutes, beats. That's subject to interpretation. Chord progressions are just written left to right. So here, C1 would be played first, then C2. These do not overlap. We also have modulation symbols, and for the non-musically inclined, these will change the key for the Roman numerals. So if I'm in the key of C right now, and I see a 1 chord, I can play this. But if my next chord is also a 1 chord, but occurring in one of these modulation contexts, such as M5, then so if this was my first 1 chord, my next 1 chord would actually be this. And we use parentheses to denote these modulation groupings. So even though the chord progression is written sequentially like this, it's actually a tree structure. So for the formal grammar definition, our non-terminals are the set of all chords with all possible durations, and that is infinite, since the duration can be any real number. The terminals consist of all of the non-terminals and the modulation symbols. Again, infinite. The start symbol is really the only finite thing here, and that's just we start with a 1 chord of whatever duration we want to generate, whether this is 8 measures of music or 8 minutes of music. Now what allows us to deal with these infinite things are the fact that our rules are functions of duration from chords to chord progressions. So I have some examples here, and you'll note that each one of them is tagged with probability. I want to emphasize that these are stochastic or probabilistic grammars. So each non-terminal has multiple rules that can be applied to it. So let's look at the first one. So here we have a 1 chord of some duration, and it's going to be replaced with a 5 chord and another 1 chord, each with half of the input duration. The second chord replaces a 5 chord with a modulated section. You can have do nothing or identity rules that leave a chord unchanged. And then this is the really interesting one. So we introduce this let notation to account for repetition in music. So if you see the phrase here, let x equal 5, 1 in XX, that means that when this expression is evaluated, the phrase would be 5, 1, 5, 1, where this 5 chord and this 5 chord are exactly the same, and similarly for the 1 chords. In music, these things are kind of standard looking things. This is a very weird thing to most music theorists, but it's a very nifty PL idea that works well in this context. Alright, so a little bit of Haskell. So in each of these cases I'm showing the implementation and some of the original definitions that you just looked at on the right. So Roman numerals are just a data type, modulation symbols are just a data type, a chord is a Roman numeral with a duration, and to capture progressions, I mentioned that even though they can be written sequentially, that they're a tree, we define a tree-like structure to capture them. We call that term. So a term can either be a chord, it can be a sequence of terms, it can be a modulated term, it can be one of these let expressions where in the math we would write let x equal a in b, and that in Haskell just becomes let x a b. A little bit shorter. And that's so. Now we have everything that we need to write progressions. Let's look at some rules. So the first thing I should point out, just for simplicity in this code, we defined some shorthand functions over here using this rule fun type. Again, rules are functions of duration. So to avoid writing repeatedly chord something something, chord something something, if we just want single Roman numerals, just write lowercase 1. For any music people in the audience, this has nothing to do with chord quality. Alright, so here are some more rule examples. So remember our identity or do nothing rules. Well, those are really easy to write. So we use this colon arrow data constructor to be able to pattern match against the left sides of rules when we need to look them up. So we'll write this by just one chord, we give it a probability, and there's our rule fun on the other side that takes the duration. The rest of the rules don't look too different from the math. The main one that looks a bit different is this one. Let expressions in Haskell become a little bit ugly to read, especially when you get nested let expressions, so I won't be showing you any of those. So the takeaway from this is that our math for the grammar deals with functions. This makes a really nice Haskell implementation. But we can't just stop with the grammar. We need to do something with that grammar. For our generative algorithm, we use a monad for that. I'm not going to show that to you. It's just easier and faster to show it pictorially, but it's very similar to the state monad in Haskell. So we start with our start symbol, which is a one chord of whatever duration we want to generate. So to give you some audio to go along with this, I'm going to map each one of these Roman numerals to a single block chord. So I'm doing very rudimentary musical interpretation. So we'll start with this. Pretty boring. So we toss our random coin to apply a rule to this, and we decide to apply the rule, replace 1 with 251, and then we get this. So now we have more than one chord in the sequence. The algorithm proceeds a lot like an L system, and just goes left to right over the sequence, tossing a random coin and applying a rule. So for the next iteration down here, the rules that happened to be applied were an identity rule, which does nothing to the 2 chord. We replace the 5 chord with a modulated section, and we do nothing to the remaining 1 chord. Now, because I'm mapping these to block chords, this won't actually sound any different from what you just heard. But the next iteration will. So down here, last iteration for the slide, once again we toss the random coin. We're not going to do anything to the 2 chord. For the next 2 coin tosses, we end up with the same rule being applied to both this chord and this chord. So we end up with a 5-1-5-1. But because this 5-1 is in the context of a modulation, this is going to sound different. So this is what we end up with. And just one last note on the generative algorithm. If you're wondering about the let expressions and how those are handled, those aren't really touched. For something like let x equal a in b, we have 2 progressions there, the a progression and the b progression. This algorithm is run independently on each of those, and any time it encounters a variable instance, that's left alone. So the generation happens, you stop after some number of iterations, and then before you can hear the result, you would need to evaluate all of those let expressions and instantiate all of the variables. Alright, so that's enough, well, almost enough math and Haskell. We'd like to hear this stuff. Block chords are pretty boring. So we need to do some kind of musical interpretation, and that's where a lot of the style is really created. So, note at the bottom here. Chord spaces are an important part of how our system determines style. So, what are those? Very briefly, they're just a mathematical way of grouping chords in musically useful ways. And our previous work on the subject shows that you can take a Roman numeral and go find the bucket of concrete chords that it belongs to, and then just pick a member out of that bucket that suits your needs for the particular application. That explanation is a lot simpler than the actual implementation for working with these things, which gets pretty ugly, but I'm not gonna cover that today. So, what this does is it turns the part of the musical interpretation problem into a pathfinding and constraint satisfaction problem, which is neat, and the let expressions actually make that a little bit easier, and here's how. So let's think about this expression, let x equal pq in xx. P and q are some Roman numerals, doesn't matter which one. And if we were to evaluate that, we would end up with pq, pq. So our chord space is trivially small for this example. P can be mapped to either A or B, and Q can be mapped to either C or D. So if we were to pass the evaluated expression to a constraint satisfaction algorithm, and not tell it anything other than that, we'd end up searching through this. We'd have to go through 64 things if we wanted to explore all of them, and only 4 of them actually satisfy the original let expression. So why not do part of the constraint satisfaction on these unevaluated expressions? If you approach it that way, I won't have time to get into too many details on how we do that. You can just hop from one let satisfying solution to another using chord spaces, and you don't even have to evaluate anything in between. So let's actually hear some stuff. Alright, so this is a single pass through the system with no extra musical post-processing. I want to emphasize that. Abstract chords are going in, concrete chords are coming out. I would argue that they are better than block chords, but they're still chords, so that is why it still sounds like chords and not more complex music. So the interesting takeaway here is that the let expressions have created this interesting nested repeating structure. And when that is totally absent from music, it sounds sort of directionless and weird. Here are a couple more examples from the same system. And here's one using a different type of chord space that we call jazz spaces. So instead of mapping Roman numerals to something like this, we would map it to maybe something like that. But that still sounds like chords. Now here we get to the interesting stuff that I couldn't actually put in the paper because it's too long. So here's an example of what you get when you add this post-processing I'm calling basic foreground generation. All that means is that we're taking very blocky things like we had here and fiddling with them a little bit to add little melodic elements here and there. So here's an example of that. And just for really quick comparison, here's a short excerpt from a Bach chorale recorded under the same circumstances, which is to say, no volume changes, just performed by the computer. Pretty similar, in fact. But what? Nope. That is the score exactly as Bach wrote it. Recorded at the same tempo and all that stuff. It's just truncated short of for time purposes. But lest you think we're stuck in classical music, we're not. Different front end, different result. And again, we're going to change the front end, use some jazz chord spaces this time, and get this. So, even though this system has a definite classical bias in terms of how the grammar is constructed and things like that, it has the capability to produce a lot of different styles of music if you do things like change the chord space and change whatever you do after the chord space. So, wrapping up, this functional approach to modeling music that we've taken with this system, in addition to making some pretty nice sounding stuff, we also get a very elegant Haskell implementation that is online if you want to look at it. And by incorporating concepts like this PL idea of let expressions, it lets us capture repetition in music, which is absent from a lot of other models trying to do this sort of thing. Chord spaces let us change the style of the music pretty drastically, and but we're not done there. There are some definite directions for future work. The most obvious one is melody, which is not directly supported at this point. The foreground generation for the classical examples added some melodic elements, but this is not a pop ballad melody that you would sing. So that needs to be added into the system somehow. It would also be nice to have more diverse rhythmic support. Everything you just heard is in 4/4. It would be nice to be able to do a waltz or even something like triplets in 4/4. I do actually know how to solve that problem. I just haven't done it yet. That will be what I start on after this. It'd be nice to have some more complex developmental patterns modeled. Repetition is great, but musicians don't do just that. In fact, they very rarely do exact repetition. It's much more common to have a phrase almost completely repeated with some subtle difference. So there are a lot of styles of music that are fundamentally based on this, like theme variations. You can't do theme variations in the system right now. But it would be nice to be able to add that capability. And finally, I've been getting a lot of interest from people recently in doing empirical testing with human subjects using this system to do some sort of indistinguishability test or goodness evaluation. How well is a particular style reproduced? How do people respond when they hear this music versus music produced by actual humans? So with that, I'm done. You can go get the implementation if you want to look at it. Generate some crazy things with it if you want. For the recordings where I just played segments of them, those are online on SoundCloud, and that's it. Thank you. Yes. Okay, so I will now summarize the question. So the question is, this system is exclusively top-down, and musicians do not work this way. So is there a way to, once we have some hierarchical structure, allow some kind of communication between the leaves to get a more realistic sounding result? And so obviously the current system cannot do this, and I do not believe context-free extensions to this system would be able to do it. But I'm working on a context-sensitive extension. So one thing that was suggested to me at ICMC last month on a similar system that I presented was to actually alternate the generative step with something else, doing very much something like that. That, you know, let's generate something top down and then think about it. So that's one possibility. The other possibility would be to have context sensitivity and rules that can rewrite or undo things, which would be an interesting direction to explore. So yes, those are very much on my mind for future directions for this. Okay, so the question was, how am I choosing the probabilities for the rules, right? Okay. So this might be a little bit too small to see in the back. This is a complete listing of the rules. I should point out that the right-hand sides of the rules, not necessarily the durations, but the chord selections, I just ripped those out of a Schenkerian analysis book. And there aren't very many of them. The probabilities, you'll notice, here are all our rules for 1. That's very uniform. Some of them are a little more biased, so like I would prefer to keep a 2-chord the same than to make it some sort of weird modulated section, because those don't sound very good. What I did when creating these probabilities was not really very inspired by any theory or anything more significant than that. I started out with uniform, and then because I wanted to see everything in action, and then I just tweaked it very little to try to avoid having rules applied too much if they tend to sound bad when that happens. So one thing I am working on right now is actually driving these production probabilities through machine learning. So that I actually have a prototype of that. It has analyzed the bot corral. So that's where I will be going with the probabilities. But these are all just done by hand and not using a very sophisticated approach. Mm-hmm. Okay, so the question is, did I consider doing probabilistic programming? I'm not, either this is a term I'm not familiar with, or it's already the approach I'm doing. I'm not sure. Okay, I'll assume I answered that. I'm confused, but that's okay. Just a minute. No, the answer is I have looked at those. I just haven't done anything yet. Yes, I have a prototype. I have a prototype that does that. It's just yes. Repeat the question, please. And the question was. Given a genre of music, can you infer both the production probabilities and the grammar of music? I hope so. I can infer the production probabilities right now. Getting the actual rules out is a little messier. This is part of my ongoing dissertation work, but yes, I hope so.